So we start with Matteo giving a presentation on a propositional dynamic logic for choreographies.
Oh, yes. Good morning, everyone.
While we have a second, we didn't. We are going to have on the web page of the workshop some information for the social dinner. Okay.
So, I usually give the last talk of the day every time, and now I'm the first one. It's quite, and I usually get rid of all the technical detail because I'm the last of the day. But now I have to use another excuse, and let's say that too many, and we don't want to see. But there is a preprint online if you want to see all the technical detail. But what I want to give you is an overview of what we have done and why, especially why. And it doesn't work anymore. Oh, okay. No. Okay, so of course it's joint work with Fabrizio Montesi that you may have seen, and Marco Peressotti there. And again, just some motivation of this work, and then I will explain you, or give you a simple presentation of propositional dynamic logic if you've never seen before. And then the problem that we found in the application that we want to have for the propositional dynamic logic, so what we cooked as solution to our problem, and some remark and future work. So let's start with motivation. And as Fabrizio told, people were interested in understanding internet data flow, and Fabrizio wrote a project. He won the grant, and I get paid with the grant. And the mission of the grant was empowering citizens in gaining agency about their private data and by building technology which is accessible and actionable. It corresponds, no? So said differently, we just wanted to find a way to distinguish protocols used in internet and explain people what are the real difference. And by distinguish, the project is mostly interested to distinguish with respect to the data which are communicated online because of privacy reasons. So as soon as you want to distinguish program, the first thing that you can think is, okay, we take by simulation, and for example, these are two programs that you can think the dot as the state of the program, and the arrows are the transition, and you can see that these two programs are the same because you can perform the same transition and whenever you reach a state. But the problem is that we do not want to just talk about the possible execution that you can do, the possible action, but we want also to be able to express that after you perform one action, one instruction of the program, then some knowledge has been changed, especially the knowledge of the agents of the system. And the way to tackle the problem was, okay, let's see what people in security does, because it's the same kind of problem. Instead of trying to understand if a message which is supposed to be secret has been shared, here the message that we are interested in are private data, so let's try to use the same techniques. So there are a lot of work on that, and the main tool user are dynamic logic because we want this evolution of the program, and some epistemic reasoning because you want to build up a knowledge of the participant to the network that can be used or exploited by the attacker and see if the protocol has some vulnerability. And generally you work with expression of this type, which you can read like in a state S reached by the program, there is a sequence of action such that in this case, I'm able to decrypt the message. So you see these are, we'll talk later, but these are, it's called diamond, which are labeled by the action of our program. So we want to represent something like this. So let's take what has been done in the last 50 years now. And let's say propositional dynamic logic as starting framework just to be able to express property about programs. And the idea of propositional dynamic logic is that you mix the propositional reasoning, you see that you have some propositional atoms, conjunction, disjunction, with programs which you represent inside these modalities, which is the box and the diamond. And the program in PDL usually are considered as a legal language generated by some elementary action. And the idea is that programs in PDL are essentially, you can think a program as coinciding with the set of its traces. And again, what is the point of having the program here? And the interpretation is pretty simple, is that you have the usual interpretation as in classical logic. If you have a conjunction, it's true only if both of the conjunction are true, and the disjunction is the same. But here the interesting part is the meaning of programs, and you say that box alpha phi is true as formula if whenever you execute the program alpha, no matter which execution of the program alpha, phi holds. And the interpretation of the diamond, if that exists a possible execution on alpha such that phi holds. So and usually what you do is that instead of doing like in classical logic, in which every formula is even true or false, what you do is you build a Kripke frame, it's called. So it's a model in which you have, the easiest way to think is that you build a model for each state of the program. And in each model, you have an evaluation function tell if a formula is true or false. And then you use the programs as a reachability relation between the words. And for example, you can express property like this one, which I'm saying that this formula is true if either for every time that you can execute beta or gamma, p is true after executing them, or there exists a way, sequence in which you execute alpha and then beta, or alpha and then gamma, such that p is true. So for example, here, this model do not satisfy this formula because you can see that here, of course, you can execute either alpha and then beta or alpha and then gamma, and you have one of the options in which p is true. Here, you are executing beta is true. Here you are executing gamma, beta, and p holds. But here you cannot execute beta or gamma and reach always a word in which p is true. Because here you have an option in which you can execute gamma and then p do not hold. This is the intuitive idea of PDL. And you see that here, in some sense, you have the words, which are the state of the system, and now you can put some propositional reasoning inside the logic itself. Now, what is the problem is that there were no solution suitable to have some kind of PDL working for concurrent programs. And in the literature, there are some partial solution, but the main problem is that there are no solutions which are the parallel, the true concurrency part, the interleaving, and the recursion are handled at the same time. And there was another possible tool at our disposal, which is a paper from who? Montesi and Peressotti. Eva is also here, and Luis, which use OR logic, which is from the 69, but let's say that OR logic you can easily represent as a small part of PDL. And the problem of using OR logic is that you can only express formula of this shape, and you see that there you have a box. And in the example that I've given you from the existence of a possible attack to a security protocol, I had a diamond. This because when you want to check security property, to have one possible failure of the security property is enough to say that the protocol is not secure. So that's why you want diamonds and you do not want boxes. So what's the problem there? Why nobody had a suitable solution? And the problem is, as I mentioned at the beginning, PDL, the programs are just regular languages, and said in algebraic way, clean linear. And as soon as you put some commutation in clean algebra, and the commutation and the thing that you want to represent this interleaving concurrency, you have an undecidability problem even to decide if two expressions are equal. This was quite confusing for me, because if you come from algebra, finite algebra, and ring and groups, monoids, as soon as you have commutation, everything becomes simpler. But here, because you have recursion and because you have choice, it's a totally mess. So, so in some sense, any possible idea of extending, having a concurrent PDL is doomed to fail. And the problem is that here, what PDL does, it's essentially reason about the traces of the program. And so, what if we separate the trace reasoning from the operational semantics of the program? So such way, if a program has a problem of the operational semantics, it's not our fault, but we can continue reasoning on traces like we do in PDL, usually. So this was the simple idea behind what we have done. So to take usual axiomatization of PDL and add some axiom which represent the operational semantics of the program. And the idea is that what we do is that we interpret the box alpha of phi as essentially we perform the atomic instruction of the program. So every time I want to execute the program, I just put out one of the possible instruction that I can execute. And now, in some sense, the trace reasoning is on the green part of the program, and not on the red part. So in some sense, I'm encapsulating the problem of the operational semantics in 1 hour place, and I'm pulling one instruction of the time from the program. Such a way, I can use PDL, and I can use the operational semantics. So what we have done then is, OK, there was a recent paper in which they come out with the sequent calculus for PDL. We added additional rules to model this new axiom that we added, and we proved that we have cut elimination, but you may not be interested with technical result. But the fact is that we have a sequent calculus for this logic. That means that you can automatize reasoning by implementing a proof search algorithm to deduce property on the programs. And I was too fast. But we have a lot of time for questions. So the idea is that, as I told you, what we have done is that in this more general framework, we recover PDL as a simple instantiation in which essentially we have an operational semantics on the clean algebra, which is something pretty natural. It interprets the sequentiality as sequentiality and the choice as choice, but in the O plus, not the plus way. And for example, what we can do is that we can simply implement this operational PDL with the CCS. And what you have is just you take the semantics of CCS and you plug inside this logic. And the only thing to do is that almost nothing is that you have to consider the silent action as the natural element of the clean algebra with respect to the sequential composition, of course. And interesting, there were some work in the literature in this direction, but there were some problems that they were not able to use the parallel composition as supposed. The work in the literature only used the parallel at the top level. And most of them just rely on the fact that you can interpret P parallel with Q as P followed by Q or plus Q followed by P. And the problem is that when you do that, of course, you have an exponential blow up of any representation of the program and any test of program. And most of them, they do not they really use recursion, but more iteration. And the reason is because in clean algebra, you have an operator which is an iteration, is not recursion. So the idea of the previous work was, okay, we take PDL, and in the clean algebra, we add the parallel operator. And as I told you, there are problems there. And then, since this is a workshop on choreographic programming, we can now plug choreographic reasoning inside propositional dynamic logic. And I think you all know how choreography works. And now we have at least the basic level of what were the initial motivation of the work. So now we have essentially we have this new toy. What we can do is that once we formalize the result in this new logic, because if we want application, we have to be sure that everything works, we can add the epistemic reasoning. So now what we can do is that in the propositional dynamic logic, we can start to add proposition, which talks about the knowledge of the participant in the protocol. And what you can do, what you can expect is that if I give you a choreography, I'm able, in some sense, to predict all the knowledge in the limit of the reasonable, to have a way to extract the possible knowledge of the participant after I will execute the choreography. And then we can start to use result on differential privacy to say, okay, if this is the common knowledge in the network, what can be inferred by this knowledge locally? And have back to the solution of the initial problem, and maybe have, instead of just telling the user what are the endpoint of the message exchanged by cookies, we may be also able to give some insight of some derivative knowledge which can come from the fact that you granted some information to one website and to another website, but they may communicate, and maybe by knowing just a part of information, they're able to know something else. And thank you for your attention, and if you have any question, we have 3 minutes.
Working? Okay. We are open to questions. If there are none, I can do you have one? Yeah.
Hello? Okay. Hi, Matteo.
Hi.
So I just want to make sure that I understand kind of the application of this work to choreographies. So if I understood correctly, you're saying given a choreographic program and given a predicate that's like P knows this, Q knows this, R knows this at the same time, you're asking, can we find if there's an execution that will reach that state where we all have the same knowledge at the same time?
So what you can write now is that, for example, for any execution of the choreography using the box with the choreography inside, let's say true, then P knows something, Q knows something else, and R knows something different. And now you can formalize this inside the same logic, and you have an inference system which should be able, if the problem is undecidable, so you cannot go any further, but if this configuration is reachable, should be able to show you a proof that this configuration is reachable.
So specifically, if they can know those things at the same time, right? Because otherwise you can just execute the choreography and see if after a certain amount of time they have that.
Yeah, there is also another problem that knowledge may not be monotone, because, for example, what you do, you communicate that, for example, a variable on a value on a variable, but then the choreography will update the variable. So that's kind of non-monotonic reasoning is still beyond what we have done. Oh. But again, to have all this reasoning, all this epistemic knowledge, we should have at least a way to be able to express. And what we have done, we create the way to express this kind of properties.
Can you Do you have a clear idea how differential privacy would be used in such a system?
So my idea is that once that you have a way to say from the execution of this choreography that exists, or any execution of this choreography will lead on a situation which the participant has this kind of knowledge. Now you can use this, let's say, base of knowledge of the participant to then build up an expert system on that. So for example, if you know that P now knows your address and your name, and now it knows your complete address, this is quite easily. But for example, you can use result on differential privacy that they know that you're EP, they know that you visit that website, and there were results, for example, based on your web history, they were able to deduce your address, something like this.
Oh, so this would be extending what is knowable.
Yes, yes, yes. So it's
okay.
This is the first layer. Now, on top of this layer, we can now use this base of knowledge to build up to the reasoning using differential privacy results. But the problem was, okay, how can I be sure that after executing, I have this configuration of knowledge in the system? So what PDL is needed here is to be able to be sure that you can have this configuration of knowledge on which you can reason.
Cool.
Maybe this is a not so smart question. Why is decidable equality important? That was the reason for having the operational dynamic logic.
It's the same problem of halting problem. You want to know when the program ends. So here you want to know, it's a pretty simple question. I'm telling, is it true that every time that I execute A and B, I can have the same results? So it's a way to say that A and B are equal. And in this setting is undecidable. And I think it's also undecidable by simulation in general. So it's just to say we are not solving all the problems of the world here. You still have the problems that are outside.
Thank you.
Okay, thank you very much for the presentation and your questions.